Yes, thank you, Matt. And then good morning, good afternoon, good evening. Thank you all for joining us for the Thermal Transport Cafe. My name is Jeff Waymeyer, and I'm an assistant professor at Rice University. I'm chairing the session today, and it's my great pleasure to introduce Dr. Alekos Garivalis, who is coming to us from University of Pisa at Italy. So Alekos did his PhD also at Pisa, working with Professor DeMarco, doing some really exciting work about fundamentals of boiling and evaporation assisted by an external electric field, and particularly in reduced gravity environments. So we're going to be hearing today about some very exciting experiments in a variety of reduced gravity environments that are providing a lot of insight into the fundamental mechanisms and also potential applications for the electric forces in two-phase flows in reduced gravity environments. And for his work, Alekos has received a number of awards and a great deal of attention. And for example, he received the 2024 Eurotherm Young Scientist Award for his doctoral work. So please join me in welcoming Alekos. So we'll hand the floor over to him, and then we'll have some time at the end for Q&A as well. Thank you.
Okay, thank you very much, Jeff. And I want to thank also Matteo for inviting me. So let me share my screen. Okay, can you see the presentation?
Yes, looks great.
Okay, perfect. So welcome everybody. Today in this talk, I'm going to present you some of the experiments that I've been involved in the past years, and so I will discuss about boiling and drop evaporation in the presence of an external electric field. And the electric field serves as an enhancement technique. And the first observation of electric field with bubbles and drops when fluids in general were performed by people like Faraday or Lord Kelvin. But we see that there is the first patent talking about electromagnetic field as a transfer enhancement is by Chubb, 1916. And he applies voltage between the surface and water to obtain enhanced heat transfer in heat exchangers. So it's one moment. Of course, we did the test before. Type screen share. Okay. So the first, okay, the electric field. We are going to discuss the common topic to all my sections in the following is the electric field, which is it can be used as an enhancement technique in the electrohydrodynamics field. And this happens because the electric field in presence of fluids arises, some volumetric force arises in the fluids, and these forces are commonly divided in three terms. The first one is the electrophoretic force, which is due to the charges, to the electric charges. This rho F is the electric charge density. E is the electric field vector. And then we have two components, which are the electrophoretic and electrostatic forces, which are basically due on gradients of the electric permittivity. And so if we define a volume of fluid, for instance, inside an electric field surrounded by the surface F, we can define the electric force as the volumetric integral of the volumetric force expressed there. But this, for the Gauss theorem, can also be expressed using Maxwell's stress tensor. So in heat transfer, we can have some enhancement due to electroconvection, due to charges. So charges are moved in the fluid and induce some motion in the fluid, but also electroconvection due to the gradients of the electric permittivity, for instance. Such is shown in the equation on the left. In two-phase, then we have some interfaces, such as the liquid and vapor interface. And so we have a very strong gradient of electric permittivity. So we have some electric stresses arising at the interfaces. So for example, bubble dynamics is modified. We have some instabilities at the interfaces, such as at the critical heat flux and in the film boiling, or like in Taylor cones, and also some synergistic effects with other enhancement techniques, such we will see in a few slides. This technique has a noticeable application, since in reduced gravity environments, we can use effectively this technique to mimic and replace gravity force, for instance. So in my presentation, I will discuss and talk about 4 of the research projects and experiments that I've been involved in the past years. The first one will be the effect of the electric field on single vapor bubbles in microgravity environment. The experiment is Ruby. The second topic is the droplet evaporation in microgravity with electric field. This was conducted on sounding rockets. And then I will show you some boiling enhancement using microstructures coupled with electric field during parabolic flights. And finally, I will give you some details of our recent work of boiling under electric field using high resolution diagnostics. So let's start with the first topic. Ruby project, namely reference multiscaling boiling investigation, is the first European boiling experiment on board the International Space Station. You see on the right here the shoebox, which is Ruby, a small experiment that was contained in the Columbus module of the International Space Station, and this project aimed to investigate bubbles in microgravity, since bubbles grow slower and became larger, so we have higher spatial and temporal resolution. And without gravity, we can investigate better natural stresses such as static pressure and capillary force, and imposed stresses such as shear stress and electrostatic stress, which is the topic we're interested in. We conducted this long-term experiment on board the International Space Station. So having many bubbles produced inside the experimental facility with a large parameter range, and ensuring also repetition, which is very difficult to obtain in microgravity facilities. This project started early in 2008, but the experimental facility was launched on 2019, when I was just starting my PhD. And experiments were performed during 2 measurement campaigns between 2019 and 21. So there is a previous talk, Thermal Transport Cafe, on January 18, 2022, that was held by Dr. Silaf, who explained quite well all the details about Ruby. I'm going to limit only to the electric field part. So Ruby, this is the schematic of the test section, the test cell. It is a cell filled with FC72 liquid. It is an electric fluid in which a bubble grows from an heated substrate, which is represented also here, and it is nucleated from an artificially etched nucleation site. Laser initiate the bubble growth, and then the bubble is recorded using a black and white infrared camera for 10 seconds. You see here, this is again Ruby. The test section is this small part here with this round window for the camera. And we performed 100 of sets of parameters. So the experiments are divided in 4 kinds. We have the unperturbed boiling, and then especially we're interested in pool boiling with electric field. These numbers here are the number of data sets, so changing the boundary conditions, and they were repeated at least 3 times each. So I'm going to focus on the electric field experiments. So as you can see here, we can set different fluid pressure, subcooling, heat flux, and so on. But to apply the electric field, we use this special electrode, which has this particular shape. As you can see, in the proximity of the nucleation site, there is a nearly uniform electric field applied between the electrode and the substrate itself. So how the experiment look like? So here on the left, you see a spherical unperturbed bubble growing in microgravity. As you can see, the bubble does not detach and grows in a quasi-static way. When we apply the electric field with the electrode, we see that the bubbles are elongated vertically, and most importantly, they detach. They detach with a certain frequency, and so the electric field is able to remove bubbles and vapor from the substrate. We investigated different electric field intensities. So you can see, for example, here, for the same parameters, for the same pressure, subcooling, heat flux, and so on, the only difference is the voltage applied to the electrode, so the electric field intensity. And as you can see, all the geometrical properties of the bubbles are tracked in time with a dedicated software using MATLAB. And from the analysis of this black and white movies, we can measure all the geometrical parameters of the bubble, including the interface. But for instance, we see that the growth is with a constant contact angle. The contact angle increase with electric field. Also, the base diameter of the bubble increase with electric field. So the bubble without electric field would be a spherical cup. With electric field, we have the elongation, increasing contact angle, increasing base diameter, such as in this picture. The electric field increases the contact angle, but contact angle is also heat flux dependent, and this was measured during these campaigns. Concerning bubble detachment volume for a fixed electrode position is non-dependent on heat flux. It is mostly dependent on the electric field level. But of course, if you see the detachment frequency here on the right, it increases with the heat flux, since the energy per unit time that the bubbles provided to the bubble is increased, so the vaporization rate increased. But concerning the bubble grow rate, we show that the bubble is thermally controlled grow rate, and you can see that the grow rate of the bubble itself is reduced with electric field. This is probably because there is some electroconvection in the surrounding of the bubble, so a higher part of it is transferred towards the liquid directly. So, but most importantly, we show that there is a detachment effect, and the detachment volume is dependent basically on the electric field intensity. So to investigate the detachment mechanism, this is a work which is reported in my PhD thesis. We performed a force balance of the bubble. And so starting from the black and white movies, we were able to evaluate some geometrical properties such as contact angle, height, the base diameter, and so on, and the entire profile of the bubble. And so the schematic of the forces acting on the bubble is this one. So we have the overpressure force that acts at the bubble base and is due to the imbalance of the pressure between the inside and outside of the bubble. Then we have the surface tension force due to the surface tension at the bubble base. In general, we could have buoyancy, this term here, but in the International Space Station, this term is negligible. In principle, we could have also some inertia, viscous, lift, drag forces, and all other kind of forces, but it has been evaluated that all these forces are negligible for our experimental conditions. And so we can calculate all these forces here and have the imbalance of all the forces, which is the resultant force, and we can compare this experimental force with the electric force that is provided by the definition. So we calculated with electric stress tensor. I have to give you some more details here, because to calculate the overpressure force, this is an interesting topic, how to define and calculate this the overpressure force. So the difference between the internal and external pressure. And to do this, I started from the interface balance. So this is a small piece of liquid vapor interface we can consider. And those are all the actions, the stress Newton on square meter acting on the interface. And so we have the external pressure and the internal pressure. We can say that those are the mechanical pressures. Then we have the surface tension. And also here, the yellow arrows represent the electric stress. The electric stresses can be calculated knowing the Maxwell stress tensor. And all we have to know is the electric field distribution at the two sides of the interface. So this is the balance in the normal direction of the interface. So we have all the elements that are represented in the sketch. And so you see that the pressure difference from inside and outside the interface is balanced by the surface tension, and the R here is the radius of curvature of the interface, and the electric stress difference at the interface. That if we know the electric field distribution, we can calculate it. So in general, I should add the hydrostatic head here. This term with the gravity acceleration is the difference between point 0, at which I perform the interface balance, and point number 1 here at the base of the bubble. But since gravity is negligible on the International Space Station, this term is not here for this in these conditions. And so in my thesis and other works, I defined the pressure force in this way. So including this one is the sigma is the surface tension, R is the radius of curvature at the apex of the bubble, and there is also this term in red, which should be included let's say to have a better physical insight of what's happening to the bubble, but it requires numerical or analytical evaluation of the electric field in order to calculate this delta F, as I show you in the previous slide. And the electric force in this definition is simply the force that that comes from the integration of the Maxwell stress tensor around the bubble, the volume of the bubble. In former, another definition that has been used by me as well is this one. So if we define the pressure force, simply moving this term in the electric force, this can be done, and we can evaluate this the pressure force only from geometrical parameters. But in my opinion, this gives less physical insight of what is happening, especially this force balance definition that requires the numerical evaluation of electric field has been also used for sessile drops, and it is coherent and gives some expected and reliable physical results. But in any case, we can use this is just a matter of definition of forces. So concerning the Ruby experiment, as I said, I have to know how the electric field components at the interface, and to do this, I used a FEM, finite element method software, which is COMSOL. And so this profile of the bubble that you see in this movie is the experimental profile that I obtained from the black and white movies. And using COMSOL and solving the electrostatic equation, I can have the electric field in each point of the space. And so since I have the electric field at the interface especially, I can use the definition of the forces that I presented you before. And you will see in this plot an example of the output. So this is the forces acting on a bubble as a function of time for a run of the Rubik experiment. You see here there are 5 bubble detachments. The blue force is the pressure force. The red one is the surface tension force. And the yellow one is the resultant force. It is the imbalance between the pressure and surface tension force. As I said, buoyancy force is negligible, and also all the inertia and drag forces and so on are negligible. The black dots represent the electric force calculated using COMSOL and using the definition of the Maxwell stress tensor. So there is a good match. And so we can say that in these conditions, we are, let's say, we are considering all the forces that are actually acting on the bubble. If we plot the same forces that I showed you before as a function of volume, we see an interesting thing. So we see that first of all, the force is negative. This means that the electric force tends to push the bubbles towards the substrate and press the bubbles towards the solid substrate. And the module of the force, so the force increases with volume up to about 15 cubic millimeters. At this stage, there is the force start to stabilize and then increase to a certain point at which then the electric force flips, and at this moment, at the last volume is about 25 cubic millimeters, there is the detachment of the bubble. And so this effect, this fact that the force changes direction is due to the fact that bubble enters in a region of non-uniform electric field, which is represented by the hole of the electrode. So since the bubble is far from the hole, since the bubble is in a nearly uniform electric field, the force presses the bubbles toward the substrate. But it is important that when the bubble enters in a non-uniform region of the electric field, there is the reversion of the force sign and also the detachment. I can show you some other movies here. And these are interesting because these movies are in the same conditions, so pressure, subcooling, and so on. The only thing that changes is that on the left, we have an aperture boiling experiment, and then we have the same average electric field, but the electrodes at a different distance from the substrate. So you see on the right here, with the electrode close to the substrate, there is the regular detachment. But if the electrode is higher, we see that there is no detachment, but the bubble starts to slide laterally. In any case, the effect of the electric field is the vapor removal. In this movie, the conditions are the same, except that we are increasing a bit the heat flux. Now it's 0.75 watts on centimeter square. And we see that again, with the electrode at 6 millimeters, there is detachment. With the electrode at 8.5 millimeters, there is no detachment, and you see that this last bubble tries to get inside the electrode hole, but it is stuck due to the high volume. Finally, if we consider this another test at 1.5 watts on centimeter square, so we increase again the heat flux, we will see that bubbles will. And in this case, you see in the middle movie with the electrode at 8.5 millimeters. At a certain point, bubbles start to grow from two different nucleation sites. This is unexpected, but you see that the bubbles, in any case, if they cannot detach, they slide laterally. In any case, they are removed from the heated substrate. This is because vapor bubbles tend to go towards the regions of lower electric field. That could be the electrode hole, but also at the lateral side of the electrode, we have, again, a region with lower electric field intensity. So the vapor tends to go in the opposite direction of the gradient of the electric field intensity. I want to show you that in this work that we did it was joint work together with Mattia Bucci, Mateusz Zupancic, and Axel. We define the forces in a let's say in a slightly different way compared to the to the equation that I showed you before, but we obtained the same conclusions. And especially we deepen a bit the detachment mechanism, because I don't want you to remember that the electric force changes sign, and so we have the bubble detachment. We see that we have what we call the onset of departure. So the onset of departure is when the base radius of the bubble starts to decrease, stop increasing monotonically and start to decrease. So this is the onset on departure is before the reversing the change of sign of the electric force. So we have this the onset of departure, and then we have here the electric force, which is this one with the light blue one, is starts to increase, and then it is reversed. And only after this stage, so even after this stage of the change of sign of the electric force, we have the actual detachment. So the detachment mechanism is more complicated than a simple flip on the electric force sign. So to summarize what came out from this research, we measured and we quantified the change in the interface shape of the bubble due to the electric stress. We observed that the growth rate is reduced, and this is due to electroconvection. Especially, we verified and showed that vapor removal are promoted. Vapor removal is promoted in these cases. Oh, sorry. Sorry. Okay. The vapor removal is promoted, and this can occur with the detachment or bubble agitation that occurs with a slide, lateral slide of the bubble. The electric force, as I said, were calculated. They push the bubble towards the substrate, but they can also contribute to the detachment due to the high non-uniformities. Okay, so this was more or less what we studied regarding the electric field in microgravity for the Ruby experiment. Of course, there are some other aspects that have been studied within the Ruby project. But now I want to change topic and go to the droplet evaporation with electric field in microgravity, because always during my PhD, another experiment was carried out, this time on board a sounding rocket. And the project is named Advanced Research on Liquid Evaporation in Space. So this is a research project with the aim to study the evaporation of droplets in microgravity. And the aims were to investigate the Marangoni effect, so thermal effects on the evaporation rate, the effect of an electric field, the instabilities at the liquid interface, and the deposition of graphene after the evaporation of droplets. So even in this RLS project was really an experiment with several objectives, but I'm going to talk about only the electric field aspects. So on a sounding rocket, we can obtain 6.4 minutes of very good microgravity level. And this sounding rocket R1 was launched on June 2019 from northern Sweden. And we have 5 drops that evaporated for about 30 seconds each. The experimental apparatus is this one. So you see there is this big chamber in which there is nitrogen at 1 bar. Inside this big chamber, we see the substrate on which the droplets are injected through this hole. Droplets are made of HFE 700, which is the electric fluid as well. And this substrate is kept at constant temperature, 28 degrees, while the nitrogen, the ambient temperature is 26. And droplets are left evaporating in microgravity and also in the presence of the electric field, which is applied again with this ring electrode here. Okay. We use a Mach-Zehnder interferometer to measure the vapor fraction, the vapor distribution around the droplet. So we have these windows for the laser and camera to access and to obtain an interferometry of the gas vapor phase surrounding the droplet. So here there are the 4 droplets. I will neglect for this presentation droplet number 1 and number 2. We can concentrate on droplet number 3 and number 4. They were produced at exactly the same conditions. The only difference is that the first one is without electric field. The other one is in the presence of the electric field. So starting from and processing the interferometry data, we could potentially measure the mole fraction of the vapor surrounding the droplet. Unfortunately, due to the fact that the vapor cloud was outside the field of view of the camera, we could not have the quantitative measurement of the mole fraction of the vapor. But still, we could have these lines that represent the vapor concentration isolines, so they can give us the shape of the vapor cloud surrounding the droplet. Here you see the droplet without electric field. The vapor cloud does not assume a spherical shape typical of the diffusion of the vapor, but it is elongated. This happens because there is a strong marangoni inside the liquid that affects the vapor cloud and change the shape of the vapor cloud in such a way. So you see that if you make this droplet evaporating in microgravity, you will see vertically elongated vapor cloud due to thermal effect, due to marangoni effect. But if we apply the electric field here on the right, you see that the vapor cloud is not more vertical, it is flattened towards the substrate. And this is very similar to what happens in normal gravity. You can see here and also here. Normal gravity without electric field. So the electric force in this case on the vapor surrounding a droplet has the same effect of gravity. And this happens because electric forces rises in the gas vapor phase due to the gradients of electric permittivity, which is not due to the temperature difference, but to the vapor concentration. So we have nitrogen and vapor, and the electric permittivity, since there is a gradient of HFE vapor, there is a gradient in electric permittivity, so we have some electric forces. In this publication, we were able to numerically simulate what we observed experimentally. So we are pretty, even if we were not able to reconstruct completely the mole fraction, we are pretty sure of the physics. And at the end of the story, we have the electric field here acts as an enhancement factor. So it's kind of mimicking the gravity. So we have about 20% enhancement on the evaporation rate in these conditions. And finally, we also performed the force balance on the droplet. I used the same forces definition such as in the bubbles, exactly the same definitions. And so you see here, if you look at this plot on the bottom right of the slide, you see that we have the pressure force in blue, the surface tension force in red, and in green we have the resultant force, which is the imbalance of the other two forces. And in black, this is square blacks, this is the electric force calculated within COMSOL. So the same model that was developed and applied for the bubbles was successfully applied also on droplets. And so I think that it can be applied with liquid vapor interfaces in general. And as you can see here, the pressure force, it is reduced compared to a spherical drop. This is a spherical drop, it means that with no electric field. So with no electric field, we would have a higher pressure force that balances the the surface tension force. But here the pressure force is reduced with the electric field, since the electric force is pushing the droplet upwards in this case. So it is pushing the bubble not towards the substrate, but towards the electrode. And it helps the pressure force to balance, let's say, the surface tension force. So, okay, summary of this experiment is that, so we verify the force balance on a droplet, a liquid droplet. We also see some modification of the interface shape of the droplet. And we notice that the vapor of HFE is influenced by the electric field. So we have this enhancement effect on the evaporation rate, since we are kind of mimic what happens in gravity conditions. And we successfully simulated numerically what happens, and this matched quite well the experimental observations. Okay, these two parts deal with my PhD, my doctoral work. And I will shift back, come back to boiling. So I briefly show you some results of fundamental single bubbles. And we also applied the electric field in reduced gravity environment with boiling experiment, coupling the electric field with microstructures. So you see here, this is a boiling in microgravity, and on the right you see the kind of microstructures that we used. So microstructures are, has been proved that they are very good enhancement technique for boiling. They rely mostly on capillary pressure, which is kind of independent on gravity. And so we wanted to test these structures in microgravity environment, and also verify the synergistic effect that occur using both microstructures and electric field. So to do this, again, we have a boiling cell. I'm not going to explain in detail here, but we have a boiling cell in which we can control pressure and temperature. And for this experiment, we use again FC72, the electric fluid. And with a metal grid, we applied the electric field above the boiling surfaces. So we have two different experimental setups. The first one here on the top was developed together with Matteo Bucci group, and it flew on the parabolic flights campaign 71. And then we used the same apparatus with some other structures from our colleagues from Xiangjiantong University, the group of Professor Wei. Also, we tested this also in reduced gravity, in partial gravity. But still, the boiling surface is 1 centimeter by 1 centimeter, and this is the metal grid that applies the electric field above the boiling surface. Okay, there are some differences. The microstructures are both etched on silicon, but the main difference is the size. So if the size of the structures by MIT are about 5-10 microns, the structures of the Chinese group are about 30, 60, 120 microns. So they are almost 100 of magnitude higher. And so what we did is to perform and to record some boiling curves on board the parabolic flights. Parabolic flight is another microgravity facility that allows about 22 seconds of microgravity during a parabola. We also have some experiments on Moon and Mars gravity, so we can have a bit more, 24 and 33 seconds of reduced gravity level. What is the difference? So if you see boiling on Earth, it looks like this. So we have on the top the smooth surface, on the bottom the microstructural surface, and the first column is without electric field, the second column is with electric field. So despite some differences in the bubbles that look a bit more elongated, such as in Ruby, you don't see much difference. But the difference is at least from the boiling pattern. The boiling curve has some differences, but the boiling pattern not so much. But you see that in microgravity, without electric field, you will see a very big bubble lying above the substrate, and small bubbles that grow and tend to merge inside the big bubble. When the electric field is applied, however, we are able to break the large bubble and obtain this kind of boiling patterns here. And what happens concerning the boiling curves? So not much effect on the heat transfer coefficient. So all the curves, if you see, are overlapped, but the biggest difference is the critical heat flux value. And you see that in microgravity, it could be quite reduced. But if you apply the electric field, we can restore the critical heat flux value to reasonable values. This is on the right is the difference between the smooth surface, here the black curves, and the microstructured surfaces, the colored points. So again, the microstructures have an effect on the transfer coefficient, and the microgravity, the gravity level affects mostly the critical heat flux. So I have to speed up a bit, so I will skip this. Just to show you that the different conditions, there are some movies, let's say, this is very close to the critical heat flux, and you see that there are some differences in microgravity and with and without electric field. And this is for the same heat flux condition, you will see the difference in the boiling patterns due to the different gravity level. We measure the critical heat flux at different conditions, so using different surfaces, microstructural surfaces, both in microgravity and in Earth gravity. And I will go to the next plot. So you see here, we have critical heat flux without electric field, and this is the microgravity condition. And we see that for the microstructures, the small microstructures provided by the MIT, even without electric field, we have a certain increase in the critical heat flux. This point here is the smooth surface. And even without electric field, we have an increase of critical heat flux. So it means that the capillary pressure or the mechanism that works on Earth is working also in microgravity. This here is the same values, but at Earth gravity. And applying the electric field, we have a larger enhancement. So it means that there is the synergistic effect. The electric field is capable to remove the vapor from the heated substrate. And so there is a synergistic effect with the microstructures that can work together to obtain even higher enhancement. And this did not happen with the larger microstructures from the Xiang-Jiantong group, because as you see, in microgravity, even with the microstructures, we have almost the same electric field value, but the synergistic effect is present since if we apply the electric field, we have very high values of the critical heat flux. And this value is higher than this one, which is the value of the smooth surface. So this means that electric field is capable to work in a good synergy with the microstructure as well, also for these kind of structures. And for these kind of structures, we have these nice points here, which is basically the lunar and Martian gravity. So we have also an idea of what could happen for reduced gravity level in between microgravity here and normal gravity, Earth gravity. So you have to speed up a bit. I will skip this as well, because I want to talk about our last works performed together with the MIT group, so Matteo's Bucci group, especially with Marco Graffedi. Now we have also Marco Comiso, master student from Pisa working on this topic. So we use the high resolution diagnostic available at in the Red Lab in the MIT to see to better understand and get some insight on why electric field enhances the boiling heat transfer. And to do this, we use this apparatus, which is concerning the boiling is more or less the same. So we have the boiling surface with the grid to apply the electric field, but then we have an high-speed camera to perform phase detection and the infrared camera to measure the temperature of the heater. And so from we can use, let's say, this optical technique to have the phase detection, and so we can we have the picture of the bottom of the boiling surface, and we see that the dark gray represent the liquid while the light gray represent the vapor. And so we can have these nice movies at very high speed, about 15,000 FPS. And so the first thing we observe is that in this condition with FC72, we did not observe the macro layer, but still we have the contact line and dry area information from these movies. The other device is the high-speed infrared camera that in principle that gives us the temperature field below the boiling wall, and in principle can give us the heat flux distribution by solving the inverse conduction problem. However, with this fluid and with this substrate, we are not able to resolve the heat flux. We are currently working on achieving this measurement. This is the work of Marco Graffedi and Commisso. So for this talk, I will just discuss about the phase detection. So we performed some boiling curves that you see here, and increasing the electric field. So the blue one is 0 kilovolts. So here is represented with the electric field is represented with the voltage, and the red one is the highest voltage. As you can see, the heat transfer coefficient, as for before, is not much affected by the presence of the electric field, but we have an effect on the critical heat flux. And what we can see qualitatively, but also we processed the movies to have a quantitative analysis of these pictures here, is that the higher electric field reduces the dry area fraction. So the bubbles are smaller, especially as I show you for Ruby experiment, the bubbles are elongated, are smaller, and they interact less among them. And so we use the percolation theory to calculating the probability density function of the bubble footprint area, and we verified that the boiling crisis is kind of triggered when this curve, which represents the density probability density function of the bubble footprint area, reaches this scale-free power law with an exponent which is about 2. So when in other terms, when these curves reach this dotted line here, this is the trigger of the stability, so the critical heat flux. And this happened also for these experiments. And what the electric field does is not to increase the heat transfer coefficient, but to reduce the interaction between the bubbles. So we delay the moment in which the bubbles merge in a large, let's say, vapor mass, creating a large dry area at the substrate footprint that initiate the bubble crisis. So we verified this theory here. And also, I have not time to give you details now, but we were also able to perform a mechanicistic reconstruction starting from the phase detection data, and to show that most of the heat is transferred due to quenching, so the transient conduction, and about 20% with triple contact line evaporation. So this is my last slide, because this is I show you is work which is still ongoing. So we are giving some more details, coupling the fundamentals of boiling that we learned together with these high resolution measurements to understand the enhancement principles of the electric field. And but I want to close with this slide, because I show you most of my research with electric fields, but as you can see, like most of the experiments I show you were performed with FC72, which is the perfect dielectric fluid. So it means that no significant charge accumulations occurs at the interface, and basically we do not have the Coulomb force or the electrophoretic force. So we do not have the force due to the charges that I show you in the very first slide. And this is a boiling of FC72 in the presence of electric field. And as you can see, you have this regular boiling, bubble detaches. You can see here that the bubble is elongated, such as in Ruby. But now the FC72 is out of production because it has very high global warming potential, and it is very difficult to find, since a lot of experiments were performed with this fluid by the boiling community. So we are moving towards new dielectric fluids, and like, for example, Novec 649. And in this case, I still did not find a perfect dielectric low GVP fluid. I think that most of the new fluids are they're called leak dielectric. So in this case, we have the accumulation of charges at the interface. As you can see, the boiling pattern here is more violent because there is also another term in the force. So we should study more these kind of fluids and take care that a lot of research that has been done with FC72 will be not sufficient to describe non-perfect dielectric fluids. And with this, thank you for attention. I conclude.
Great. Yes, thank you, Alekos, for the beautiful talk, and really great to see these amazing results. We have a few minutes here for questions. So folks who are interested, please go ahead and unmute yourself to ask the question, or to type your question into the chat. While folks are getting set up, I had a few questions. I was curious about the finite element simulations. Do you have to do full three-dimensional simulations for your electric field calculations during the bubble growth? Or is the problem sufficiently symmetric that you can do some simpler calculation?
Yeah, the problem is symmetric. This is why we use that kind of ring electrodes. As we're talking about Ruby and Arles, so even for the droplet. So in this case, so we could at least for the electric field, we use a symmetric domain.
Okay, nice.
Jeff, can I ask a question?
Yes, please.
So Alekos, I have a couple of questions actually on work that mostly I don't know. I was wondering, the sounding rocket, right?
Mm.
I was under the impression that the rocket will spin.
Mm-hmm. Correct, but that is the departing phase.
The parting phase only, so it doesn't.
It doesn't spin when it is in orbit. The microgravity doesn't spin. The spin is to reduce the drag with the atmosphere. So it's the same principle of the bullet.
Right.
If it spins, you reduce the drag, but it is not necessary when you are in orbit. So that there is a kind of gyroscopic brake, kind of, I think. So, but it stabilizes in the microgravity doesn't spin, so you don't have the centrifugal acceleration.
Okay, thank you for clarification. And then I have a question about slide 36, which I think is the one on the electric field and the micropillars.
Yes.
Results that probably are from
36.
Yeah, slide 36, I think.
Let me share again. This one?
No, but maybe the one before. Yeah, so this one. So how come you have such a long maybe I can try to draw, maybe not. Yeah. Is this due to the fact that you actually don't nucleate?
Sorry?
There's a delay in the nucleation?
Okay. These two curves are the smooth surface, okay? And so we are in microgravity. So without electric field, you will see that about 10 watts on centimeter squares, you have the critical heat flux. With the
Sure.
electric field, yes, you have a kind of the two curves are not overlapped, and this is so you have a kind of enhancement of the heat transfer coefficient. If you are asking me this question.
No, my question is whether or not when do you start to boil? Do you have say access to the surface, optical access to the surface?
Yes. We start to boil when the more or less when the superheat is about between 10 and 12. About 10. So there are bubbles there. There is a nucleate boiling region there.
So even in this region here, you're
Yes. I mean, nucleate boiling. You will see this kind of thing here. You will see this big mushroom bubble. You will see this. So we don't have the access actually on to what is happening close to the surface, because the big bubble is not with the big bubble is not able. We only have the lateral access, such as in these pictures here, which are our pictures, by the way. But more or less, you will see the same. So yes, actually, you see the big bubble, but not exactly what happens below. It will be interesting to have an access like a phase detection in microgravity as well.
The reason I was asking is that we typically see that kind of behavior when you have suppression of nucleation and
Yes.
So that's why I was asking. Thank you.
No. Thank you for asking, and maybe my answer was too fast because it could be that, but
Thank you.
we do not have access.
I like your work a lot, so thank you.
Thank you.
I have one question or two. Yeah, Alekos, thanks for the talk. You mentioned that you're still searching for a particularly or potentially useful dielectric fluid. Have you tested ThermaSolve, maybe? ThermaSolve's CF1 or whatever. Do you know that?
No, we did not test. We are currently testing TMC49, Novex 649, SF33, and HFE. No, but I didn't test that. Is this kind of dielectric? Could be?
Yeah, it is. I just checked on the data sheet. On ThermaSolve, it is produced by Inventec. I can send you the link later, but
Yes,
it's
please.
the electric constant and the electric strength, it's a bit higher than for the FC72, even though I don't know how leaky it is, you know, I mean, how leaky the
Yeah, for that, we should check also the electric conductivity, because to calculate relaxation time, we need electric permittivity and electric conductivity. So if you check only the permittivity, more or less will be the same, 1.76, but the big difference of the FC72 is its low thermal electrical conductivity.
Yeah.
So, but please send me, I will check. Thank you.
Yeah, I will send you. Yeah, about so the next question is how far are you now? Probably, I don't know, with Matteo or some other collaborator to actually do the electric fields on heaters which are textured and infrared transparent, so to have it all, you know, to have all information at once. So textured surfaces, electric field, infrared.
Yeah, that's a question for for Matteo's group, actually. Not so far, I think.
Oh yeah.
Don't jinx it.
Thanks. That's all.
Thank you. Thank you very much.
If we have time, I have one quick question. Can I?
Yes, please go ahead.
Okay, thanks. Alekos, thank you. Your presentation was great. One quick question. So one of your presentation slides show that when you were using electric force, you were able to see the earlier ONB earlier onset of nuclear boiling happening with the electric force. Can you tell me like what is the fundamental reason for that?
You mean the last slides, right?
I'm not sure whether it was last or not, but I was seeing
Okay.
within the boiling curve you were mentioning
Yeah,
with
yeah,
the
yeah.
electric force, OMB was earlier.
Let me share just to make sure that I understood. In this slide here.
Yeah, exactly, this one.
Okay, okay. This this is another effect, yes, I didn't mention, that can be explained as well with the electroconvection. So you reduce the overshoot because you have also electroconvection in the bulk liquid during the single phase convection before the nucleation. So we didn't investigate this much, but the answer is how, let's say, the nucleation process is affected, including the electroconvection. So I didn't deepen this particular part here, but
Okay.
I'm pretty sure that this is the explanation.
Okay, thank you.
Sorry for being very short, but I don't want to say things that I don't know.
It's okay. It's okay. It seems like by using electric force, seems like your nucleation superheat's getting decreased, but I don't know
Yeah.
whether they could be explained by just electroconvection. But yeah, thank you.
Yeah. Thank you. Yeah, it's a good point. I have to think it. I have to think about it.
Okay, I see we're getting to the top of the hour here, so I may suggest that we all thank Alekos for the wonderful talk, and thank you for joining the TTC discussion today, and thank you all.